Hello and welcome to this presentation related to simple harmonic motion. In this presentation we'll outline the underpinning theory, which can be found in standard engineering textbooks. We relate the principles of simple harmonic motion initially to a mass spring system, and we will derive relationships between displacement x, velocity v, and acceleration a. And for reference, here is some of the underpinning knowledge referred to within this presentation. There are separate presentations, if required, on each of these topics. Here's a brief overview of the nomenclature used within this presentation. X is the displacement of the body from what's termed the equilibrium position, also sometimes referred to as the mean or the mid position, that's in meters. Theta is the angle turn through in radians. Omega is the angular frequency or the angular velocity in radians per second. V is the linear velocity in meters per second. A is the linear acceleration in meters per second squared. T is the time taken to turn through angle theta, that would be in seconds. A is the amplitude of the motion in meters, and m is the mass of the body, for example the mass connected to a spring, and that's in kilograms. Here's a brief overview of the contents of the presentation. Initially we commence with illustrations of simple harmonic motion related to mass spring systems, pendulums, cams, etc. We then introduce simple harmonic motion and the conditions required for SHM using a mass spring system as an illustration. We then consider the characteristics of simple harmonic motion related to acceleration, velocity, and restoring force F. We then show a graphical representation of SHM found in some textbooks, illustrated here on the right hand side, from which we derive an array of formulae related to displacement x, velocity v, and acceleration a. We define some terminology, which includes periodic time, capital T, and frequency, lowercase f. Finally, we provide a summary of the formulae derived within the presentation and conclude with an example that shows application of some of the SHM formulae derived. For reference, here are approximate timings in minutes when the various topics of the presentation commence. You may find this useful if you want to skip to a certain topic area, or if you have prior knowledge of simple harmonic motion, you might want to jump straight to the formulae listed around 38 minutes into the presentation, and then attempt example 1, commencing 41 minutes into the presentation. For your reference, there is a second presentation where we apply the various formulae derived in this presentation to a whole series of exercises. Typical examples of where simple harmonic motion occurs in a simple spring mass system. Here we have a mass located at the edge of a spring of some stiffness, oscillates in the vertical sense with simple harmonic motion, or SHM. A simple pendulum, that's the mass on the end of the pendulum here, and for small displacements of less than 15 degrees, shown here, the pendulum oscillates with simple harmonic motion. A further illustration of simple harmonic motion is the cam and the cam follower. Here's the cam, shown here an off-centered circle, and here's the follower, and the follower moves with simple harmonic motion. Another illustration here from a car engine shows the rocker mechanism. Again, here's the cam, here's the follower, and pivoting about the rocker allows the valve to open and close here. So the cam follower moves with simple harmonic motion. Another illustration is the Scotch yoke mechanism, sometimes termed the slotted link mechanism. This is a reciprocated mechanism which converts linear motion of the slider or sometimes termed the piston is shown here, into angular motion or vice versa. Notice the crank shown here is directly coupled to the slider shown here. And here's the engine mechanism in a diagrammatic form. And again, the periodic movement of the engineering mechanism can be assumed simple harmonic motion. Again, here's the crank moving in an angular sense here, and we have the piston moving in the reciprocating linear sense between A and B. Let's consider vibrations or oscillations. Engineering mechanisms and structures are capable of vibrations. Systems that possess both mass and elasticity are termed elastic systems. The occurrence of vibrations may be very useful. For example, guitar strings oscillate and produce musical notes, or they can be harmful, as when bridge structures vibrate, from which possibly collapse can occur due to wind-excited oscillations. There have been documented occurrences of bridge collapsing as shown in figure 1 here. In most cases, oscillations are lessened with time and may recede completely due to damping effects. Damping is the resistance to the movement resulting from factors such as air resistance and friction within the vibrating system. Note that within this presentation, damping effects will be ignored. Let's define free vibrations. So free describes vibrations of elastic systems which, having commenced due to some initial disturbance, are allowed to continue unhindered. Consider the elastic system shown in figure 2, which comprises a helical spring, shown here. The mass, shown here, is oscillating about its static equilibrium position, and that's the position where the mass hangs freely when at rest or stationary. So here's the static equilibrium position, and the mass is oscillating either side of this position. Sometimes the term force vibrations is used, and force vibrations occur where a continuing disturbing force is present in the system. We will not consider force vibrations within this presentation. Let's consider simple harmonic motion, SHM for short. SHM is defined as a periodic motion when the two following conditions apply. Condition 1, the acceleration is always directed towards a fixed point in its path. And secondly, the acceleration is proportional to the distance from the fixed or the midpoint of the motion. A perfect example of SHM is the oscillation of a mass spring system, as shown in figure 3 here. The spring of natural length L here carries a mass of m kilograms. By applying the mass m here, the spring finds what's termed the equilibrium position with the mass attached. From the equilibrium position, the mass is given a further displacement labelled as x, shown here, and then released. We can see then that the mass oscillates in the vertical sense as indicated by the dashed line shown in figure 3. This is an example of simple harmonic motion. SHM theory continued. So now the mass oscillates vertically about the mean or the equilibrium position shown in the previous figure 3. And from figure 3, the following relationships can be readily determined from the mass spring system and indeed shown to apply to simple harmonic motion in general. Figure 4 here shows the relationship between displacement, labelled as x, velocity, labelled as v, and acceleration, labelled as a. So for initial displacement x of the mass from the equilibrium position, we initially will have zero velocity because it's commencing from rest, the extreme x distance from the equilibrium position, and on release of the mass, due to the spring stiffness effects, there will be an inward acceleration generated. The mass then oscillates with the variation in displacement as shown by the top diagram, essentially a cosine curve. The velocity of the mass is illustrated by this curve, basically a negative sine curve, and the acceleration of the mass follows this negative cosine curve. Notice the oscillation relates to angle theta, also denoted as omega t in radians, and repeats itself every 2 pi radians. On the next slide, we'll state the various characteristics and relationships between displacement, velocity, and acceleration. Simple harmonic motion theory continued. So the acceleration of our mass has the following characteristics. It's always directly proportional to the displacement from the mid position. The acceleration is always directed towards the equilibrium position. The acceleration is zero at the equilibrium position, and the acceleration is a maximum in the positive and negative sense at the maximum displacement in the positive and negative sense. Considering the velocity of the mass, the velocity is zero when the displacement is at its maximum in the positive and negative sense. The velocity is a maximum when the displacement is zero. In other words, we're at the equilibrium position or the mid position. And if we have an acceleration in our system, then from Newton's second law, F equals ma, there must be a force in our system, termed the restoring force here. This force is directly proportional to the displacement of the mass from the equilibrium position and always directed towards the equilibrium position. Those are the characteristics of the acceleration, so you'd expect them to be also the characteristics of the force. So here's a slide showing figure 3 and figure 4 concurrently, where we try to relate the movement of the mass spring system to the various characteristics of displacement, velocity, and acceleration. So initially we have a spring of length L. We attach a mass to the end of the spring, and it eventually settles into what's termed the equilibrium position of the spring with the mass attached, and it's stationary. Now the mass is further displaced by a distance x, and then we're going to release the mass. Notice the positive direction for x is downwards. So on our diagram we have a positive x displacement. We will have no velocity because at this point the mass is stationary. But on release of the mass we will generate an acceleration due to the stiffness of the spring and the extension of the spring. Notice again we're plotting here over one complete cycle, so that's 0 to 2 pi radians. So on release of the mass we have an acceleration due to the force in the spring. Notice on our acceleration diagram this will be a negative value because it's in the opposing direction of the positive notation we're using here. The velocity is 0 at the point of release, and of course the displacement is a maximum. If we now consider the movement of the mass spring system, it now returns towards the equilibrium position. At the equilibrium position, the value of displacement x will be 0. The velocity will actually be a maximum, but because of the direction of the velocity being opposite to our positive notation, it's a negative velocity. The acceleration at the equilibrium position will actually be 0 because the spring now has no displacement from the equilibrium position. The mass will now overshoot the equilibrium position after achieving the maximum velocity. So the mass is now overshooting and moving towards the highest point in its travel. At the highest point in the travel, the displacement now will be maximum negative displacement, and the velocity at the extreme displacement from the equilibrium position will be 0 because the mass is about to change its direction, and the acceleration now will be a maximum positive value because considering now the direction of the acceleration downwards here, that's in the positive sense to the notation used. Due to the compressive force in the spring, the mass is now forced back towards the equilibrium position. Again, at the equilibrium position, the displacement x will again be 0. The velocity will actually be a maximum, considering the positive direction of the velocity to our sign convention. And again, at the equilibrium position, the acceleration will be 0. The mass now again overshoots the mid position and returns to the lowest point in the system, which is equal to the original displacement x, where the velocity is again 0. So the value of x now returns to its original position when the cycle first started. We have 0 velocity at this extreme position, and we have maximum negative acceleration. So those are the characteristics of one oscillation of the mass spring system through its 2 pi radian movement. And just for convenience, I've summarised the information on the previous slides here, showing the relationships between displacement, velocity and acceleration, and detailing their characteristics here, including the restoring force. Let's consider a graphical representation of SHM. In figure 5, shown here, which is a circular representation of SHM, OP, shown here, is a radius having a length A, shown here. OP is considered to be rotating uniformly with a constant angular velocity about fixed point O, shown here, which is the intersection of the reference axes labelled OX, and OY. The angular velocity, labelled as omega, also sometimes termed the angular frequency of OP, has the SI unit of radian per second. Here's omega. OX is the reference axis from which OP has rotated through angle theta, shown here, radians, in t seconds. So from angular velocity, omega is equal to angle turned through divided by time taken. This equation can be arranged to find the angle turned through. Theta is equal to omega multiplied by t. Call that equation 1 for reference. Let's consider the motion of point M in figure 5. So this point here on our graphical representation. From the right angled triangle OPM in figure 5, so this right angled triangle here, OPM, we can derive the expression for displacement x as a multiplied by cos of theta. So in other words, dimension x, distance from the midpoint to M, is a cos theta, and that's from basic trig, knowing that cos theta is the adjacent side divided by the hypotenuse. So that's a cos theta in this case. If we now substitute equation 1 for theta, remember equation 1 was theta is equal to omega t, we can write the displacement x as a cos omega t, called that equation 2 here. If we now differentiate equation 2 with respect to time t, we form the differential equation dx by dt is equal to a multiplied by, in brackets, negative omega multiplied by the sine of omega t. Notice that cos omega t is the standard form cos ax, and when differentiating cos ax, the solution is negative a multiplied by sine ax, where in this case the a is our omega and the x is t. And noting that dx by dt is actually linear velocity v of our midpoint M, we can write the equation for v as equal to negative a omega multiplied by sine omega t. I've called that equation 3 for reference. Just note that the negative sign indicates the velocity of the body is towards the mid position O on our diagram. So for the position shown at angle theta and our direction of omega here, the velocity v would actually be negative to the convention shown on the diagram. If we now differentiate again with respect to time t, we form the equation dv by dt, and again using the standard form, this time for sine ax, we form the expression negative a omega multiplied by, in brackets, omega cos omega t. As I said, that's from the standard form of sine ax when differentiated becomes a cos ax. Noting that dv by dt is actually linear acceleration a of point M, we can form equation 4, a is equal to negative a omega squared multiplied by cos omega t. Notice the negative sign indicates that the acceleration of the body is towards the mid position O. So our acceleration sense is opposite to that shown on our graphical representation here. So the motion of point P continued. Just repeated equations 2, 3 and 4 from the previous slide for convenience. So we now have equation 2 used to find displacement x, equation 3 used to find velocity v, and equation 4 used to find acceleration a for any particular value of time t. From above, if we substitute equation 2 into equation 4, it produces the following expression for linear acceleration a, and that is a is equal to negative omega squared multiplied by x. Call that equation 5 for reference. In other words, x replaces the a cos omega t terms. And as the term omega squared is a constant, we have a constant angular velocity or angular frequency in our questions, equation 5 states that acceleration at point M is proportional to the displacement x from the fixed point O on our previous diagram. And that's a characteristic of simple harmonic motion, that the acceleration is proportional to the displacement from the mid position. Repeated equation 5 for convenience here. There's a few comments on the above equations. positive displacement x of point M is measured from O on our diagram here to the right along the horizontal axis. So that's a positive x here. Velocity v and acceleration a of point M must also be taken as positive in the same direction as x, as indicated in figure 5 above. Positive v, positive a. For position x shown in figure 5, x is positive, so equation 5 here will indicate that the acceleration a is negative. Hence the acceleration a of point M is towards the fixed point O. This condition, together with the fact that the acceleration is proportional to the displacement, means that point M moves with simple harmonic motion. Here's a slide showing the graphical model, but for two different positions of phasor OP. On the left-hand diagram, phasor OP is shown in this position, measured angle θ1 on this horizontal axis, and point M, the projection of P on the horizontal axis, has a positive displacement labelled x1. So for this diagram, displacement x1 is positive, but the linear velocity v would be negative, and also the linear acceleration a is negative. As due to the position of the crank OP and the direction of the angular velocity, the linear velocity of m is towards the mid position, and for a simple harmonic motion, the acceleration is always directed towards the mid or equilibrium position. In other words, against our positive notations shown on the diagram. If we now consider the right-hand diagram, phasor OP is in this position, angle θ2, again measured from this axis, and point M, the projection of P on the horizontal axis, is now at x2, but to the notation, x2 is now a negative value. However, at this position, the velocity would be positive, because M is now moving towards the mid position, and the acceleration would also be positive, as the acceleration is always inward seeking towards the equilibrium position. So that's just two instances to show how phasor OP moves to different positions during the periodic cycle, and how the displacement, velocity and acceleration values change their senses. Let's develop another equation related to simple harmonic motion by applying Pythagoras' theorem to the triangle OPM in figure 6. Here's figure 6. Here's our right angled triangle OPM. Applying Pythagoras' theorem to the triangle, square of the hypotenuse, OP squared, is equal to the sum of the squares of the other two sides, so that's OM squared, and added to PM squared. But note that length OP is actually amplitude A, in other words the maximum displacement in the motion. Also that displacement OM is actually dimension x here. So we could rewrite Pythagoras' theorem in this instance as A squared is equal to x squared plus the PM squared. Rearranging the equation for PM, that's equal to the square root of, in brackets, a squared minus x squared, and I've called that equation 1 in Roman numerals. We can also apply basic trigonometry to this right angled triangle, noting that the sine of angle theta is equal to the opposite side PM divided by the hypotenuse A, and also recalling from equation 1 we derived previously, the angle theta is actually equal to omega t. So we could replace the theta in our equation here with omega t. So now we have the sine of omega t is equal to Pm divided by A. Again, rearranging the equation, Pm is equal to A multiplied by the sine of omega t. Call that equation 2 in Roman numerals. If we now equate equations 1 and 2, Roman numerals, we have A multiplied by the sine omega t is equal to the square root of A squared minus x squared. Call that equation 3 in Roman numerals. If we now substitute the equation 3 in Roman numerals into equation 3 we derived previously and shown here for convenience, we can derive the equation velocity v is equal to minus omega multiplied by the square root of a squared minus x squared. I've called that equation 6 here. So another equation for calculating the linear velocity of point M when moving with simple harmonic motion. And just note for reference, when evaluating a square root, this term here, there are always two solutions. That is always a positive and negative answer. So equation 6 can be written as shown below. V is equal to positive and negative omega multiplied by the square root of a squared minus x squared. A more general format for equation 6. Now, often in textbooks, this equation for velocity is written in the positive sense only. And finally, for reference, if we want to calculate the maximum linear velocity, that occurs when displacement x is equal to 0. In other words, no displacement from the mid position. Thus, equation 6 simplifies to V max is equal to positive and negative omega A. Let's consider some terminology associated with periodic motion. We have considered some of these terms previously in our mathematical presentation related to sinusoidal forms, but they're briefly outlined again here for reference. The term cycle, sometimes also termed an oscillation, that's the motion completed during one period, i.e. the to and fro motion about the mid position or the equilibrium position of the body, shown in figure 7 here. Here's the mid position, and the body oscillates about this mid position. Considering our mass spring system, a cycle also occurs when a mass descends from its highest position to its lowest position and returns to the highest position. Terminology continued. The amplitude often given symbol capital A, is the maximum positive or negative displacement x of the motion from the mid or the equilibrium position. So in this case, here's our equilibrium position, and our maximum amplitude is shown as A here. Either side of the equilibrium position. The periodic time, or sometimes simply referred to as the period. Periodic time has the capital T notation, and it's the time that elapses whilst the motion is repeating itself. So the time it takes for one cycle to occur, and most oscillatory motion is repeated in equal time intervals, hence the term periodic. Terminology continued. Frequency, usually symbol lowercase f, is a number of cycles that are completed in a unit time period. And note that a system performing free vibrations will oscillate at its natural frequency. The SI unit of frequency is the hertz, Hz, and equates to 1 cycle per second. Note that frequency is the reciprocal of periodic time. So lowercase f is equal to 1 upon the capital T. I've got that equation 8 here. So conversely, periodic time t can be stated as t is equal to 1 upon f. Equation 9 here. Let's consider frequency, periodic time and angular velocity or angular frequency. Considering the SHM motion as a projection of a point moving uniformly in a circular path, shown in figure 9 here. Then from figure 9, the time taken for M here to complete one cycle is the same as the time required for OP, shown here, to complete one revolution. So if OP makes omega radians in 1 second, omega shown here, then we can say that OP makes 1 radian in 1 upon omega seconds. Or OP makes 2 pi radians in 2 pi upon omega seconds. We know from our work on radian measure that 2 pi radians is 1 revolution, and that time for 1 revolution of OP is the periodic time t. So our periodic time can be written as 2 pi upon the angular frequency, or t is equal to 2 pi upon omega. Call that equation 10. So a relationship there for periodic time in terms of angular frequency or angular velocity omega, and of course if we know periodic time, we also know frequency because it's a reciprocal of periodic time. Consider our relationships between frequency, periodic time and angular frequency. With reference to equation 5, repeated here for convenience, we could rearrange the equation 5 to make omega equals to the square root of a divided by x, transposing equation 5 here. And knowing that equation 10, periodic time, is 2 pi upon omega, we could replace the omega with the square root of a divided by x. So it would be 2 pi upon the square root of a divided by x, or we could write that as t is equal to 2 pi the square root of x divided by a, equation 11. And again, recalling our relationships between periodic time t and frequency f, we know they're reciprocal of each other. So if t is 2 pi upon omega, then frequency is omega upon 2 pi, angular frequency upon 2 pi. So we also have an equation for frequency in terms of omega. It's omega divided by 2 pi, equation 12 here. And again, using equation 5 shown above, we can write frequency, equation 12, in terms of a and x. So it becomes 1 upon 2 pi multiplied by the square root of a divided by x, equation 13. So we've generated a raft of equations on the previous slides, and they're summarised here for reference. So this is all the formulae relating to simple harmonic motion. Equations 1 through to equation 13 derived previously. So a reference slide that we can use for later calculations considering problems that involve simple harmonic motion. Summary of formulae relating to SHM continued. Here's a summary of the nomenclature used with the appropriate unit for each quantity. Note as always, angles are used in radians, and in dynamics all dimensions must be in meters. One aspect I particularly like of the graphical representation of SHM, shown in figure 5, is that from a mechanical engineering perspective, the rotation of the phasor OP of length A, which equates to the amplitude of the motion, is totally analogous in mechanical engineering to a Scotch yoke mechanism, where the crank OP rotates with the same motion, omega, as phasor OP in figure 5, and the radius of the crank OP is of course the maximum throw of the motion of the slider. In figure 5, it's a projection of P onto the horizontal point M here that is moving with simple harmonic motion as the phasor OP rotates one complete revolution. So point M makes one complete horizontal cycle across the x-axis. This is analogous to point P on the crank projected onto the horizontal axis. And of course, as the crank moves one complete revolution, so point M moves horizontally with simple harmonic motion. So the slider here is moving with simple harmonic motion. So a nice analogy between the graphical model that represents simple harmonic motion and a mechanical mechanism where the slider moves with simple harmonic motion. Let's consider example 1. The crank of a machine's reciprocating mechanism is 60 millimeters long, and it rotates at a constant angular velocity or constant speed of 120 rpm. We're asked to calculate A, the acceleration and the velocity of the slider when it's 40 millimeters from the midpoint of travel or the equilibrium position. Part B, we're asked to calculate the maximum acceleration. Part C, the maximum velocity. Part D, the periodic time. And Part E, the frequency. I'd encourage you to stop the presentation and attempt example 1. Here are the list of equations 1 to 13 that we derived in the previous part of this lecture, some of which we'll now be using within example 1. However, the full work solution is shown on the following slides. So example 1. Firstly, extract the information from the question. The angular velocity, capital omega here, is 120 rpm. That's the constant speed stated in the question. The angular velocity, lowercase omega, in radians per second. That's 120 multiplied by 2 pi divided by 60, so 12.57 radians per second. Or in pi radians, that's 4 pi radians per second. The amplitude, symbol A, is 60 millimeters. That's the length of the reciprocating mechanism. So converted to meters, 0.06 meters. And the displacement from the midpoint of travel, we're given in the question here, that's symbol X, is initially 40 millimeters. Again, converting that into meters. So part A, we're asked to calculate the acceleration and the velocity of the slider when it is 40 millimeters from the mid position. Here's our mid position, and the slider point M on our diagram is 0.04 meters from it. I've drawn it to the right hand side here. So part A, to calculate the acceleration, we know from our previous work the acceleration is negative omega squared multiplied by x. The omega value above, it's 12.57. That's multiplied by distance x given in the question of 0.04. So we can calculate the acceleration. It's negative 6.32 meters per second squared. Negative because it will be opposing the positive direction on our graphical illustration here. And we also need to calculate the linear velocity of point M, v here. And that's negative omega multiplied by the square root of a squared minus x squared. Again, we have omega, we have our amplitude, 0.06 meters, and we have displacement x, 0.04 meters. So we can work out the velocity is negative 0.562 meters per second. And again, negative because that's opposing our positive direction on our graphical illustration. Example 1, solution continued. Part B, we have to determine the maximum acceleration. So part B, the maximum acceleration occurs at the maximum displacement. So that's when x is equal to 0.06 meters. So from our previous derivation, the maximum acceleration in this case will be the negative omega squared multiplied by x, where x is equal to a. Thus a max simplifies to negative omega squared a in this case. So our omega is 12.57 radians per second. The x, which is actually the amplitude, is 0.06 meters in this case. So we can calculate the maximum acceleration in meters per second squared. And part C wants us to calculate the maximum velocity. And the maximum velocity would occur when the displacement is 0, in other words at the mid position, so x is equal to 0 in this case. Thus in this case, V max is equal to negative omega A. We have an equation for velocity. It's the negative omega multiplied by the square root of a squared minus x squared. But this time the x is equal to 0. So inserting the values, we can calculate the maximum velocity in meters per second. Obviously, these values of maximum acceleration and velocity can be positive or negative depending on which side of the equilibrium position point O M occurs. Example 1, solution continued. Part D, we have to calculate the periodic time. So part D, we're calculating periodic time capital T. That's the time for one oscillation to occur. So when M transverses from the right hand side to the left hand side and then back again to the right hand side. So capital T, periodic time, the formula is 2 pi divided by omega. We know omega is 12.57, so 2 pi divided by 12.57. So 0.5 seconds. It takes half a second for point M to move from the right hand side here to the left hand side and then back again. Frequency is lowercase f, that's the number of oscillations per second. And we know from our previous work that the frequency is the reciprocal of periodic time, so 1 divided by 0.5 in this case. So 2 Hertz or 2 cycles per second is the frequency. So that concludes this presentation. There's a following presentation where we will undertake many more questions applying the various equations that we derived in this presentation. Here's the bibliography used to help generate the presentation, and I hope it's been of interest to you, and thank you for viewing.